Hello, and welcome to this lecture on Geographic Information Systems Fundamentals. The learning objectives for this lecture are to understand the components of GIS, understand the concept of layers in GIS, be familiar with common GIS functions, and understand some of the limitations of GIS. To understand what a GIS is, let's first take a closer look at what the acronym means. Remove the G from GIS and you have IS, or an information system. Information systems have been defined as combinations of hardware, software, data, knowledge, and people connected through networks. Additionally, like any system, which is a whole constructed of parts, a GIS can also be viewed as an amalgam of several parts that create the overall system. In the following slide, I discuss these parts further. The parts of GIS are as follows. Software that is used for running GIS operations. For example, commercial GIS software packages such as ESRI's ArcMap or open source web mapping environments such as OpenLayers. Hardware that is the platform in which software is run and/or data is stored. In today's increasingly interconnected world, hardware can range from traditional PCs to smartphones to massive computing infrastructures for hosting cloud computing resources. People that work with GIS in a variety of capacities, such as using GIS to make decisions. Knowledge, which is perhaps the most abstract part of GIS, but is equally important as the other parts. Knowledge, in the context of this discussion, refers to the variety of training, education, skills, and experience that are applicable to GIS. For example, by watching this video, you are gaining new knowledge in GIS. Data, which will always be the most important component of a GIS. And finally, the network, which can be considered the element that connects all the other parts together. For example, the internet that connects people to GIS data websites, or connecting GIS software with web-based data surfaces, or social networks that connect people who use GIS with one another through things like GIS user communities. This figure depicts a graphical representation of the components of GIS using a disaster management example. The core power of GIS is its ability to organize data into one common geographic view. The key thing that GIS provides to the organization of data geographically is the concept of map layers. This figure provides a graphical representation of the concept of map layers using a disaster management example. This figure shows a selection of real GIS datasets from Manhattan, New York during 2012's Hurricane Sandy to demonstrate how map layers are combined to use GIS for disaster management tasks. For example, Imagery, providing a visual reference to the geographic region in question, the census tract layer showing population thematic characteristics, tax parcels showing who owns what buildings, a road layer that provides reference to critical infrastructure, the social media layer representing locations of people who are tweeting about the hurricane, and the hospitals layer providing reference for medical issues. The concept of map layers is not a new idea, as acetate map overlays existed for years before the advent of computers. What makes modern GIS-driven map layers so powerful is the ability to overlay any number of digital map layers together and reference to a common geography, thus allowing for entities on the layers to be viewed and analyzed together with the interactive power that GIS offers, such as quickly changing the map layer, symbology of the map layer, or any of the other GIS functions discussed later in this lecture. GIS software contains powerful tools that can serve numerous functions. The following slides discuss some of the important GIS functions. As discussed previously, data is the most important component within the overall system that is GIS. The management of data using GIS is thus a primary GIS function. Management of GIS data can come in many forms. For example, GIS is often used to create spatially referenced data. Creation of spatial data can involve many activities such as digitizing features from images. In this figure, features from an area flooded after the 2011 Fukushima tsunami in Japan are being digitized from a satellite image of the disaster zone. As can be seen in the middle left of the image, a variety of construction tools such as polygon, rectangle, and circle, and others are available to create features in two categories: flooded areas and standing structures, as can be seen above in the construction tools. On the image itself, flooded area polygons have been digitized or traced from the image and are shown as polygons with a slanted line fill, and standing structures are shown as black-filled polygons. Once GIS data is created, or while it is being created, it must be stored in some type of data repository so that it can be later queried, retrieved, disseminated, and updated. Data repositories for GIS data are diverse as GIS data itself. The top image shows one of the most basic, yet still commonly used GIS data storage formats, a comma-separated values or CSV file. In this example, place name features are stored in a CSV file. CSV files are nothing more than an ASCII-based text file where data in the file is structured using commas to define data columns, and each line in the file represents a single data record. Most often used for storing point features, specific geographic information is often represented as a decimal degree or XY coordinate. These numbers can then be parsed or read by GIS software for rendering on a map. CSV files are a common data storage format used by GIS data providers such as the U.S. Census Bureau and the United States Geological Survey. Additionally, other characters such as a pipe or tab can be used to structure text-based data like a CSV file. This figure shows a shapefile, the specific files that comprise a shapefile, and what the contents of a shapefile look like when displayed in GIS, using Rwandan provinces as an example. A shapefile is actually a collection of 3 or more files for storing vector GIS data and has been a de facto, although not official, spatial data standard for many years due to ESRI's large GIS market share and publication of the shapefile format. The shapefile is still a widely used format, and many GIS datasets published by government entities in the United States, such as the U.S. Census Bureau, still use it, and thus it is important to mention. Shapefile data can only be viewed using special software, unlike CSV files, which can be viewed using a basic text viewing program. Imagery, such as satellite or aerial imagery, is commonly used as reference data in GIS. This image shows a sample of imagery collected after the 2010 earthquake in Haiti. These images were very valuable for viewing damage done to buildings in Port-au-Prince. To view geographically referenced images requires GIS software or other software designed for handling geographically referenced imagery. This figure shows storage of GIS data in a relational database. This is a very broad category of how GIS data is stored and entails keeping geographically referenced information inside structures that normally store other types of non-geographic information. Storage of GIS data inside of relational databases is typically used in large-scale operations where there are large volumes of GIS data that have complex modeling requirements and need to be shared with many people. Most professional-grade GIS technology offers support for storing GIS data inside of relational databases, such as Microsoft SQL Server or open-source GIS enterprise database environments like shown in this figure. Analysis refers to the use of GIS to investigate geographically or spatially oriented questions or problems. An important point in this regard, too, is that GIS software contains methods or tools designed to understand spatial patterns or processes. Disaster management lends itself well for providing specific examples of GIS analysis due to the fundamentally spatial nature of disasters. For example, using a buffer tool to calculate distances from a shoreline to understand potential impacts on vulnerable populations. GIS programming refers to the use of computer programming languages to build custom software applications or tools to accomplish tasks that out-of-the-box GIS software might not be capable of accomplishing. GIS programming thus evolved to become a more specialized task requiring interdisciplinary computing and information technology, knowledge, and skills, such as computer programming, that can be matched with GIS software tasks and principles. GIS programming is still a highly valued skill, knowledge of which makes one very valuable in terms of employability. A GIS programmer may write computer code for tasks ranging from batch data processing and automation to the development of modern-day mapping mashups that use complex algorithms for integrating heterogeneous data sources to solve unique problems. This example shows JavaScript code being used with the OpenLayers API or Application Programming Interface to create a simple web map using OpenStreetMap data. This is a great example of using an API to create a custom GIS application. Much like model trains or cars give us a scaled representation of a real-world entity, modeling, in the context of GIS, is the idea of using GIS to simulate conditions in the real world to answer what-if type questions. For example, a GIS-based model could be developed to simulate possible storm surge conditions and outcome scenarios. In this example, a toxic gas cloud plume is generated using the aerial location of hazardous atmospheres, or ALOHA program, that is then imported into GIS and layered on a map to show how the plume might affect an area of interest. Map production can be seen as the final process related to the other functions previously discussed in this lecture. For example, a map can be used to represent the final results of a GIS analysis to give to a decision maker, or be used to represent different parameters, scenarios, and outcomes from GIS-based modeling to make modeling results easier to understand. Commercial desktop GIS tools come with a comprehensive tool set for supporting the process behind the art and science of cartography, as well as numerous tools for final map product outputs for printing, use as static digital graphics, or as map tiles within dynamic web-based reference maps. The rise of online mapping tools such as Google Maps is also challenging long-held conventions about cartography and map production. For example, in using a disaster management example, situation awareness maps can be quickly created by plotting point features on top of Google Earth's visible satellite imagery maps. Geocoding is the idea of taking text-based inputs such as place names or street addresses and converting them to a coordinate representation. For example, 1600 Pennsylvania Avenue, Washington, D.C. would be geocoded to 38.897881, -77.036530 in a decimal degree format. A common, everyday example of geocoding is entering the name of a place, business, or address in a tool like Google Maps that can then quickly geocode the item entered and show its location on a map. It is important to also consider the limitations of GIS. Technology in general is often seen as a miracle cure to existing problems, but it is important to manage the expectations about what GIS can do. The following are some points to keep in mind in terms of the limitations of GIS. GIS software is not a miracle technology that can automatically answer all questions. Although this may seem obvious, it is important to keep in mind that GIS is limited by numerous components of the system that comprise GIS as previously discussed. For example, The answers you get are only as good as the software used, the quality of the data used in the software, and the skills of the people operating the software, conducting the analysis, or modeling and producing the final maps. GIS can strongly support answering questions, but it is still human reasoning and critical thinking that must make final decisions. Over-reliance and expectation of the technology, coupled with lack of proper GIS education and training, and a lack of good human judgment, reasoning, and critical thinking, can all lead to dire consequences. The acquisition, creation, editing, and curation of data is the most costly aspect of GIS. Anyone who is experienced with GIS has most likely learned this lesson the hard way. If you are new to GIS, it is very important to understand the importance of data for being successful at utilizing GIS technology. GIS operations, analysis, modeling, and cartography are fundamentally data-driven. Acquiring GIS-ready data is both financially costly in terms of hours spent collecting and editing data, or perhaps spending money on purchasing GIS data from a GIS data vendor. In my own teaching experiences, I've seen many great student research project ideas fail or have to undergo major modification due to lack of data to support the investigation. If you are new to GIS, pay close attention to how you will find data that can support your investigation and how much time and possibly money you are willing to spend to acquire data. In the following, I do a live demonstration of the various components of GIS previously discussed in this lecture, so you have a clear sense of how all these items work. In this demonstration, I use a commercial GIS tool called ArcMap to illustrate to you the various components of GIS that you learned about previously in this lecture. If you follow my mouse and look on the left side, over here you can see what is called the table of contents that contains the various map layers. If you recall from earlier in this lecture, I discussed the power of GIS, its ability to present geographically referenced data as map layers. Map layers can easily be turned on and off in terms of visibility by checking these boxes. For example, if I uncheck this base data box, note how the map loses many of its map features because all of these map layers are now turned off. I also have basic map interaction tools such as pan and zoom. I'm going to zoom in on an area of interest here to demonstrate another point about GIS you learned about, creating features. In this example, you can see I turned some imagery data on. Let's say, for example, I wanted to digitize these field locations. I can use these images as reference data and use various tools to digitize and create spatially referenced data. As you can see here, I'm using my mouse to trace over a feature of interest. And with a few clicks, I have a feature digitized. In terms of analysis, I can also use GIS to answer what-if questions. So for example, turning a few layers off to make my map a little more viewable, I have some hypothetical disaster data that I've included. If I turn this on, you can see that I have modeled a toxic gas plume. If you look closely at this map, this is a major transportation route going next to a village. So it might be very important to know if a truck were to capsize or tip over here, if toxic gas were to go over this village. Now we might want to see that toxic cloud in relation to places of interest in this village. For example, if I zoom in, I might be able to tell decision makers in this town that the toxic plume, as represented by this red dotted polygon is going to affect a high school, a primary school, a community center, and a library. Very important areas that should be accounted for in the case of a disaster. As you also learned from previously in the lecture, I can do custom programming to create new applications or perhaps automate a task that I don't want to use through the regular interface. I will show you one brief example of this, again using a disaster example. I'm going to turn on a map layer right here. As you can see, is a red star that is located along an interstate. In this hypothetical example, I'm curious to know what would happen if a truck full of explosives were to accidentally detonate along this interstate. Now, normally, I can do such an analysis using tools available up here, the buffer tool, but what I'd like to show you is some GIS programming with the Python window. As you can see down here, there is a command line type interface where I can type commands in to perform analysis. So for example, I'm going to make a call to the ArcPy library and the buffer analysis tool. And many of these types of functions have an input and an output. If you look over here, you can see what this command is looking for. It wants to know which features should be buffered. So in this case, I'm going to select the explosion location. And then it's going to create a new map layer based on the buffer, so I need to give it a name. And I'm going to call it explosion output. And then I need to specify how big the buffer, or in this case, how big of a circle should be drawn with the explosion as the center point. And in this case, I'm going to say 500 feet. So I enter my command in, I hit enter, and as you can see down here, the buffer tool runs, and I get my explosion output gets added to the map automatically, 500 feet around where the explosion point was. Now, of course, I can easily change and manipulate the display of that feature simply by double-clicking on it, perhaps making it hollow, making it red, making the outline a little thicker. Okay. One last thing that I want to show you is the ability to easily make a map based on the analysis. So we used GIS programming to run a buffer command, and now we want to make a map to give to a decision maker. If I click on this tab here, the layout view, the GIS tool gives me a view that looks somewhat like a piece of paper and another set of tools that I can use for creating a map. So perhaps I want to zoom in a little closer on the feature of interest, and then if I access menus up here, I get common map elements such as a north arrow, scale bars, and title text. I can then easily print or export this map out as a graphic using tools such as export map or save as. Finally, I did want to mention that GIS comes with geocoding tools. If I go back to my map view and zoom out a little bit, let's say I want to know where specifically a given address is located. in this case in a village called Geneseo. If I type an address in, 5, and then hit enter, notice how my address of 5 Main Street, Geneseo was displayed on the map. And I can use tools, interactive tools such as Flash, or even create a labeled point on the map showing me where my geocoded address is. In this lecture, you learned about Geographic Information System fundamentals. You should now understand the individual components of the system that comprises GIS. You should also understand the concept of map layers, which is used to reference various GIS datasets to one another using common geography. Next, you were shown the various functions that GIS can do, such as data and spatial asset management, that is the core of any GIS, analysis to help answer questions and derive insight into spatial problems, programming for developing custom applications and tools to extend the capabilities of GIS, modeling for creating scaled representations of reality and to answer what-if questions, cartography, visualization, and map production, which connects modern-day GIS with the millennia-old practice of mapmaking and representation of geographic features, and geocoding, which is the idea of taking textual inputs such as an address or a place name and converting it to coordinates. Finally, you also learned a little bit about what GIS cannot do. Points important to keep in mind as you learn more about GIS and the need to manage technology expectations. The following are references used in preparing this lecture. If you enjoyed this lecture or have any comments or questions, feel free to contact me at the email address below. Thank you for watching.